Hi everyone, and welcome to another mini course of Physics Latam. Today is the first lecture of this mini course on 3D topological quantum field theories and quantum invariants of 3-manifolds by Kürşat Sözer. He's a mathematician and he earned his PhD in 2020 from Indiana University, Bloomington, under the supervision of Vladimir Turaev. After postdoctoral position at the University of Lille and EPFL, he joined McMaster University as a postdoctoral fellow in the Geometry and Topology group. His research focused on low and high dimensional topology, homotopic quantum field theories of algebra, modular categories, and way many other topics. We are very happy to have him with us today. Please remember to raise your hand at any point if you have any question, and now I'll leave you with Kürşat. Please go ahead.
Thank you for the introduction, and also I would like to thank organizers of Physics Latam, Mathematics and High Energy Physics Seminar organizers for giving me opportunity to talk and this give a lecture series on this work of our work on the survey paper that I wrote with Alexis Virelisier. But what I'm going to talk throughout this talk is no originality of mine. It's already known things. Many other people are contributed. So yeah, thank you for the opportunity to give a lecture. Okay. The first lecture is going to be, there are going to be 4 lectures. The first one is Quantum Algebra Foundations. My main reference is this book of Vladimir Turaev, who's my advisor, academic advisor, and my collaborator, Alexis Virelisier. The book, the title of the book is Monoid Categories and Topological Field Theory. And the goal of this book has 4 parts and 500 pages. The goal of today's lecture is to cover the first part completely. Of course, it's impossible to cover everything in 2 hours, but goal is to go over all these things in enough details with some examples starting from no assumption, and at the end have some understanding of basics and foundational things, structures of quantum algebra, what is called quantum algebra, kind of fusion, what is a fusion category, having idea on the definition of fusion category, modular category, what they are, and then how they are defined, and what are the relationship with other things that we know. So you say again, before starting, this is my reference, and whatever I'm going to talk, you can find there, like in more detail. Whenever you have more questions, maybe you have the understanding, you can ask me, and then if for better look at the book. This is the plan of the talk, step by step. As you can see, we start with just definition of a category. No, it's nothing. No, I don't assume anything. I don't speak anything. I don't speak any. I don't assume anything. I don't assume anything from categorical point of view. And then we will start by, we will build all these quantum algebra foundations step by step. I'm going to introduce modular categories, rigid categories, pivotal, and so on and so on. And then weighted ones, and then continue. At the end, we will see what is the center of a monoidal category, which is, in my opinion, quite a bit kind of an advanced topic. Okay. And then throughout the talk, at some point of the talk, I will bring this back and then to see where we are in this map. Okay, let's start with categories and functors. So what is a category? A category, C, consists of the following data. A class called objects, class of objects, whose elements are called objects. And whenever we pick 2 elements in this class, we have a home set. the set of morphisms from X to Y. In this case, X is called source of a morphism. Whenever we get a morphism, X is called the source of a morphism and Y is called the target of a morphism. And then whenever we have two morphisms, whose one of whose source agrees with the target of the another one, like G and F, whose source of G agrees with the target of F, then we have this composition map. Whenever we have this agreement, these things, we have this composition. And this composition is associative, must be associative. It's on the nose, just equality. Whenever we pick three of them with such compatibility on the sources and targets, whenever we are able to compose them, they must agree in any, they must be the same. And another requirement that we have for any object in this set of morphisms from X to X, we have a distinguished element called identity. And whenever we compose this identity from either left or right hand side with any other thing, that's the same thing as the morphism, that we have. So what is expected? Precisely what is expected. Next, let's see some examples of categories, some of which may be useful later, maybe some of which not. So let's consider category of sets. Objects are just sets, and morphisms are just set maps. And we have kind of subcategory. We have a notion of a subcategory, which is like a collection of objects is a subclass, and then the collection of morphism between them is closed under composition. And they still stays inside this, and then we get a subcategory. We can consider finite sets among all sets, and then we still consider the set maps. Or from commutative algebra, we can fix a commutative ring K, and we can consider modules over it, left modules or right modules, and then morphisms we can consider when we pick two modules, two maps between two modules as K-linear maps we can consider as a morphisms of this category. For any group, we can form a category. We don't like this way of thinking is taking any part of math. Like whenever we have a structure on something, we can consider its category and structure preserving morphisms. That's going to be a category. That's kind of a bird eye view, like category theory being bird eye view of mathematics. Whenever we have some structure, and then we can build a category whose objects are these elements with the structure, and the morphisms are structure preserving maps. This is of that form. For example, one can consider top elements. Objects are going to be topological spaces, and morphisms are going to be continuous maps. Or similarly, one can consider diff. Objects are diffeomorphisms. Smooth manifolds and morphisms are going to be smooth maps. Or similarly, and lastly, let's say groups. Objects are going to be groups, and maps, morphisms are going to be group homomorphisms. Or the other way to construct a group is the fixing a group. We fix a group and a commutative ring, let's say K. Elements of this group are just elements of the group. Like elements, objects of this category are elements of this fixed group, and we have as a morphism, whenever we look at the morphism of an object, it's just K. But whenever we look at whenever we consider two different objects, there is no morphism between them. There's only zero morphism between them. It's not empty, but it's zero. Or similarly, when we fix a group, we can consider its representation category, K representations, and the morphisms are interminors. Or from topology, another example in topology that is useful in the study of topological quantum field theories, that are the cobordism categories. and we can consider cobordism categories whose objects are closed. Consider cobordism category in dimension 3, whose objects are closed-oriented surfaces, and morphisms are oriented three-dimensional cobordism classes between surfaces. Here, I didn't write cobordisms, I didn't write cobordism classes, but in fact, it must be classes. So what do I mean by cobordism classes? We consider cobordism between manifolds. Let's, for example, draw. I have one surface, sigma. Let's say this is the source, and I have another surface. And this is a three-dimensional manifold. Inside, maybe there is some interesting things going on. Let's say this is W. So we consider W as a morphism from sigma to sigma prime. Well, I'm specifically giving some examples on this case because all of the compositions, the considerations are in here, are very straightforward in here. What is an identity? What is a composition? Just this is a composition of set maps, composition of linear maps, and compositions. This is clear just multiplication, and composition of interminors. They're all okay. But in this case, it's a little bit strange, maybe. It's unusual. We have cobordisms, and there we consider smooth surfaces and smooth manifolds. But whenever we have another one, let's say it goes to another surface, sigma double prime, another sigma, right? Whenever we compose them, what is composition in this category when we have cobordisms? Composition is precisely gluing along common boundary. So we need to glue these two, like this is W prime. And then we get, we glue W and W prime along sigma prime and we get a new one. But the thing is, if I don't write here, if I don't consider these cobordisms up to the diffeomorphism relative boundary, then there is a problem. There is a problem that the smooth structure on this gluing is depend up to diffeomorphism, is unique up to diffeomorphism. Otherwise, there's a problem in the composition. So we need to consider diffeomorphism class of cobordisms up to relative boundary. So this is a little bit intricate details, but it is something important when we make precise arguments. Okay. So we have examples of categories. So what is a functor? How to relate categories? A functor from a category C to D. What it does, it assigns to each object and another object of category, target category D, and to each morphism in source category, a morphism in the target category as expected, relating the corresponding source images of the sources and targets. And it satisfies the composition of the maps. That's the only structure that we have here. We have only single structure and only single object distinguished elements. So this is kind of when we define category itself as a structure, kind of a composition, and composition is associative, and a unit object, unit morphism. So it needs to preserve, when we define a functor, it must preserve the composition, structure, and identity for each object as expected. So the next step is monoidal categories. So what is a monoidal category? The motivation is, let's recall what is a monoid. Monoid is a set with an associative multiplication and two-sided unit. So it's, recall, group is a set with associative multiplication, unit, and inverses. When we don't have inverses, like when we eliminate let's look at the definition of a group, and let's disregard the necessity of having inverses. Then we get a monoid. So equivalently, a monoid is a set with an associative multiplication and two-sided unit. So its categorification, it's monoidal category. So what does this categorification means? It is not quite well-defined object, but it's roughly, one can say, or one way of defining saying categorification is equalities, replacing equalities with coherent isomorphisms. Like we have category here. Now we had, remember, here this equality and this is an equality. So this is kind of the structure of an endomorphism of a monoid in this case. And then we are going to categorify this. That means we are going to replace them coherent with coherent isomorphisms. Okay. So what is a precise definition of a monoidal category? A monoidal category is a category which is endowed with a functor from product of two categories, which is defined as usual. There's a new category. There's a new category. A functor from this new category to the initial category C, which is called the monoidal product. And it is a specified object called the unit object. And a family of isomorphisms called associativity constraints or associators, if you like. Associators. Like they measure this, they are the, remember before this was kind of, when we had morphisms at least above, this, now we have objects, these are objects, but this is like replacement of equality of the associator with isomorphism. They're coherent. And similarly, a family of isomorphisms left, which are called left unitality constraints, and a family of isomorphisms called right unitality constraint. They are precisely imitating with, if you consider this as a if you consider this taking tensor product as an operation, this is like left unit condition. And this data needs to satisfy the following two conditions. And the first one is, sorry, yeah, here I, categories, step by step. This needs to satisfy the first condition is a pentagon condition. Like we start with a 4 objects in this order, and how we go from this object to this one in 2 different ways using associators. And there's kind of a one way of doing this, and then this diagram commits. That means this composition is the same as this composition. So I try to color code them, but I will not go over them due to time limitation. I'm already going a bit slow. Maybe these things everybody know. And the second condition is that for all objects, the following triangle commutes. Whenever we take whenever we take 2 objects, we can add 1 on here, and then we can do associate and apply left identity in here or right identity on here, and it must commute. But this definition is not complete. Why? If you want to be picky, because I said family of isomorphisms. In fact, this family of isomorphisms are natural isomorphisms. So they are natural transformation. I did not define, but they are kind of relations between coherent relations between the functors, things that are relating to functors. And in this case, what is this A as a A relates which 2 functors? This is identity, it relates identity and the composition of this functor with this one. And here this one is taking, like this is going from C to C, taking an object and tessoring from the left with identity and with unit object. And this is again C to C, a functor. This is identity functor, this identity functor. This is a functor from C to C, taking an object and tessoring from right with an identity. And these must be natural, so they give more conditions, but saying natural isomorphism is enough. It's more than. So let's consider examples of monoidal categories. We had sets. Now we consider Cartesian product on sets. We have monoidal structure, and in this case, unit object is going to be any singleton, any single element set. And similarly for finite sets and for modules, what is a monoidal product is precisely taking tensor product over K, and the unit is K. And when we fix this group, elements, this is the product of the group induces the tensor monoidal structure, and identity element is precisely the identity element of the group under this product. In the case of K representations of a group, tensor product of representations is monoidal product, and trivial representation is the unit object. In this case, in the cobordism category, taking disjoint union of manifolds is monoidal product, and empty surface is the unit object. So remember, empty manifold is closed manifold of every dimension. This is maybe very boring, but it is under disjoint union, that's the unit object. So in all of these, if you look at this A, L, and R, they are all trivial. There is no interesting one. If you want to make an example without non-trivial, like what I mean by here, I forgot to say here, what do I mean by stick monoidal category? When all of these A, L, and R, they're identities. If they're all identities for every object X, Y, Z, then we call the monoidal category strict monoidal category. Okay, in these cases, they're all kind of strict monoidal categories. So we can consider, if we fix the 3 cocycle, then we perturb this category, we modify this category with this 3 cocycle, such that the associator of this new category, denoted by this one, becomes the value of these 3 elements at this 3 cocycle. And the left unital is given by this, and right unital is given by this. So which is highly non-trivial. And one can check this being associator, the fact that this diagram commutes, this is precisely this W is omega being 3 cocycle. Okay. And lastly, McMaster's coherence theorem says every diagram in a monoidal category made up of the associativity and unitality constraints commutes. So whenever we have a diagram which consists of only L, R, and A, they commute. In particular, this one is an example of it. Next, we consider monoidal functor, which is a categorification of monoid homomorphism. So what is a monoid homomorphism? It's a homomorphism between monoids that preserves the monoid structure and the unit. And in this case, when we have, better go faster, when we have two categories, and we have two monoidal categories, a monoidal functor is a functor which is endowed with a morphism from the unit of the target, an image of the unit object, and a natural transformation that relates these tensor products. And we ask this, it's to satisfy these conditions. Like the first condition is how the question that we ask, how we can relate the associator of the second category with the image of the associator. And similarly for these ones, how we can relate the image of left uniter with the image with the left uniter of the source of the target category. In the same way for the right uniter. Okay. These are all required to commute. And next, strong monoidal functor is the one, remember, a monoidal functor, not a single thing, but a triple. It's a functor and an morphism and a natural transformation. When monoidal functor is strong, if F0 is isomorphism and F2 is a natural isomorphism. It is strict when F0 is identity and F2 is identity natural transformation. An example of a monoidal, an example of a monoidal functor is a representation of a group. When we're given a representation of a group G, linear representation, then we consider the category which has a single object, and the more endomorphisms of the single object is going to be G. And when we write down what it is, it's precisely as a monoidal functor. It's precisely representation of this. Well, another example from this point of the point of view of this lecture series is a three-dimensional topological quantum field theory is a monoidal functor from the cobordism category to the category of vector spaces and linear maps. And in fact, there's going to be some adjective we will see later. It's not precisely this, but it's not far from that. The rigid categories, the next thing, we are going to define rigid categories. Before that, so we need to define what is the pairing. A pairing between two elements is a morphism from their tensor product to the unit. And a pairing is called non-degenerate if such a thing admits a inverse, that's called the inverse, such that these diagrams equal to identity. So I was planning to write it down from where to where they go, but if you write it down, I will not because of the time limitation. They go in general like this. It's one, and then sorry, or this one is going to be y x y to y. So, but we will see later when we do diagram calculus. I will go over this. Very simple. You can see when you look at this, even writing them down takes a minute. But when we learn diagram calculus, it will be super easy. And that's the main use of diagram calculus, making such equations very simpler and visual. When we are given an object of a monoidal category, its left dual is a pair where the first one is an object and second one is a non-degenerate pairing. And inverse of this thing is called a co-evaluation map. The right dual of an element is again a pair. The first one is this object, and the second one is a non-degenerate pairing, but the orders are important. That's the left evaluation, that's the right evaluation. And a category is called left rigid. A monoidal category is left rigid if every object admits a left dual. And similarly for right, and the rigid category is a monoidal category which is both left and right rigid. So here I want to emphasize on the fact that rigid category is not a structure. Monoidal category being a rigid, we are not introducing any structure. We just say every object satisfies some condition. Every object admits a dual. This is like a condition. It's like a property, not a structure. That's what I want to emphasize because that's kind of a difference between rigid category and the pivotal that we will see. Okay. And examples are finite dimensional vector spaces. This category G we have seen finite dimensional representations, COB, or projective modules. So you can see if you require things to be dual, having dual, if you want all of your objects admits dual, you need things to be finite dimensional. Like not vectors, not category of vector spaces is not rigid because infinite dimensional vector spaces do not admit duals. And same for modules. It needs to be projective module of finite type. Like finite type is crucial to be to admit a dual. So same for representation theory category. But if you go to category of representation, it's not if G is not finite, then if G is finite, it's okay. But if G is not finite, if there's some interesting infinite dimension representation, then that's not going to be invertible. That's not going to be dualizable. Going to admit dual. So what is a pivotal category? A pivotal category. A pivotal category is a rigid category. Remember, rigid category is the one that every object admits a duality. But we don't say category, when we say rigid category, we don't say every object comes equipped with its their duals. We just know they admit. For every object, we have a chance to choose this non-degenerate duality with other object. One can do it. But pivotal category is come equipped with distinguished duality, come equipped with this duality data. And more left and right duals coincide. So pivotal category is a structure. What do I mean by structure? In a pivotal category, every object has a fixed dual. There's this data. But in a rigid category, that's not the case. Rigid category, we say they admit duals. We don't fix these duals. Okay? Like another way of stating this pivotal category is a monoidal category, which is endowed with a pivotal duality. That means these are triples where X star is an object which is called a dual of X, and we have evaluation, which is a non-degenerate pairing, evaluation of this like the left duality data, and we have evaluation for right evaluation. That's again a right duality data. But as you can see, we have this data for every object. We have this data fixed. That's kind of structure. And here I write this is co-if. What we write co-if is the duality, is the inverse of this non-degenerate pairing, and co-if tilde is the inverse of this non-degenerate pairing. So in such categories, we can also take dual not only of objects but also morphisms. Given a morphism in C, that C is a pivotal category, then this composition is left dual of F. It goes from Y star to X star. And same way, this composition, this whole composition, is the definition of right dual of F. The fact that left and right duals coincide, so dual of F from left and right, they must be equal. Okay? So maybe you're already thinking about this, but the best way to think about this is vector spaces and dual of them. So everything that we are writing down, like in this case, they're kind of motivated in the definition of vector spaces and finite dimensional vector spaces. And so it is always better to have this in mind. And this is like the major example of what we have as pivotal categories. And then we are choosing duals. So we are generalizing this structure in this category. We observe this category very carefully. What do objects admit, and we try to generalize. Because all of these structures, for example, for a finite group, they admit this one also shares. Whenever we have a representation, we have its dual representation. And dual representation and normal representation, they precisely fit this structure. We can write these evaluations and co-evaluations and then write all of these equations and it works out. For example, when we consider the category of K modules and module maps, it has an object in here has a left or right dual. Not all objects are dualizable, and not all objects are admit dual, if and only if it's projective of finite type. So as you can see, admitting duals is like finite dimensionality is kind of crucial. And in this case, when they admit, when we consider this subcategory consisting of this projective modules of finite type, then these duals of objects are precisely linear duals. And the evaluations and co-evaluations are given precisely in this form, just evaluations in the linear algebra or homological algebra, if you like. Okay. Okay. So I don't know if I'm going too fast. Maybe I can slow it down. At some point, I was thinking I was going too slow, but maybe I can slow a little bit. I don't know. Does anyone have any questions so far? But let me give this definition. There is another way of defining a pivotal category. This is more kind of a refined and different looking at it. This again one should consider maybe finite dimensional vector spaces. So we say a pivotal category is a left rigid category. What does it mean? Every object admits left dual. That's what we know from the first condition. But now it says distinguish left duality. It says for any object, fix such a duality. So we fix such a duality for every object. Okay, we are kind of getting close. But remember, in the pivotal category original definition, it says, okay, we have duals, but not only for left, we also have duals for right, and they coincide. Those duals coincide. Instead of requiring right duals and they're being equal to left duality, we say there is a distinguished monoidal isomorphism from this is identity of C. And this functor is like question mark 2. This means question mark is like placeholder. It's like this goes C, like taking dual. You can formalize with this data. You can formalize this as a functor. And you can compose this again, taking dual 2 times. Well, at some point in one of the two, you need to reverse the morphisms, but it's not a big deal. So this is double dual functor, like exactly in kind of fixing identification of an object with this double dual. This is equivalent to fixing right dual or double left dual is equal to taking a right dual, which is equivalent to left dual. That's another characterization of pivotal categories in a more refined way of thinking. And so far, what we have done, we have covered the 4 topics, not quite the half, but we have covered the four topics, categories and functors. We introduce categories and then we equip them monoidal structures, and we consider dualities. And this, remember, this is a structure. Again, I want to emphasize this. So this is a kind of a property. A rigid category is the one that every object admits left and right duals. We only know they admit it. In the pivotal category, we say they come equipped and their duals agree. Left and right duals agree, and we have this dual data fixed in the pivotal category. On the other hand, rigid category says they are dualizable. That's all. We don't know. We don't fix their duals. I don't know. Is there any questions? Maybe I can go these two and then stop for the first part. Maybe going slower. Okay, now there is this world of graphical calculus and quantum algebra, which is super important and making things very simple in the computational side, because otherwise writing equations very complex, as we have already seen in the case of duality. What does, remember, let's go, because we will see it again. I want you to remind, what is a pairing? A pairing between two objects is a morphism, but the condition of this pairing being non-degenerate is about this equation, these two conditions. And they're a little bit ugly. They're not the hardest equations to write it down. But if you consider more and more, this is just a definition of a simple thing. if you consider more and more condition, and if you want to prove things especially, you have to concatenate, unite, add up this type of things many times. But with graphical calculus, it becomes very simple. So in a category, let's go step by step as we did at the beginning. If we have a category, we have an object. Identity morphism is just a straight line. That's our notation. And when we have a morphism from object X to object Y in a category C, then we denote it as like box below X to Y. So we are reading from down to up. Our direction is going up. When we have composition, we just apply G above. So when we have a monoidal category, then we, in addition to composition, we have tensor product. We have monoidal product. So when we pick two morphisms, their monoidal product is just concatenation of these representations nearby, putting nearby in the order they are given. The order is important. Or if F is, let's say here, well, even if I use the same symbol above, in this case, F is X, so Y to A, B, C. Such a morphism can be written differently. This representation is not unique. We can write it as X, it goes from X tensor Y to A tensor B tensor B, or we can consider B tensor C as an object, as object itself and A, or we can consider X tensor Y as an object. So in the level of objects, we can, taking tensor product, we can just make a one string. So these three qualities, they represent the same equation, they represent the same morphism F in the category. So how about unit object? Remember, in a monoidal category, we are in a monoidal category and we have unit object. Unit object in the graphical calculus is not denoted. We don't have anything for it. So if we have a morphism from 1 to 1, like there is no string attached. There is no strings for the unit object. We don't put 1 on the strings. We just remove it to make it simplified. If we have a morphism from unit object to X, it's denoted like this. If we have a morphism from X and an object to unit object, we denote it like this. We don't put bar and then write. And because of F, the monoidality, the functoriality of this monoidal product, it doesn't matter like how to go from up and down. These are all equal. We can apply, this is composition of identity tensor G, F identity, but this is precisely F tensor G. This is condition of monoidal product. And remember, non-degenerate, we have a pairing. This being non-degenerate is precisely having omega, remember, right? This is equal to, there exists omega from 1 to Y tensor X. And those equations that I showed you a minute ago is precisely comes into these equations. We go from Y tensor 1 and we apply omega in this part. And then we apply this part and then omega in this part, and then this is going to be equal to identity of Y, and the same way for this equation. These two equations are visual representations of what we had before, which are much nicer. And I said, but not prove that uniqueness of the inverses. I said the inverses is unique. How to prove it? The proof is as simple as this one. Let omega prime is another one. Okay, is another inverse of blue, so it satisfies these conditions. So we start with this omega prime, and then we know that this is we have this is identity, right? By this is identity by this one, identity of x. We replace this by this one using this equation. And next we do shifting on the levels. Now we are in here. Now using this equation, this is identity of y. So what we have seen is it's unique. And this is the proof. This is literally the proof of this uniqueness of inverses of pairings, non-degenerate pairings. And how about the left dual homomorphism? Remember, I said in a pivotal category or left rigid rigid category equipped with duals, we can take a dual of an object, not only dual of an object, but also morphism. Okay, when we are given a morphism from x to y, its dual is defined like this. We take y, evaluation of y, and then we put f in the middle, and then take co-evaluation of x on the left. There's a left duality, and this is definition of duality of the morphism. Now, when we have a pivotal category, when C is a pivotal category, so what does it mean? It comes equipped with the dual data. We equip our diagrams, graphical calculus with arrows. Before, all arrows, we didn't have any arrows, but we now have arrows like going down. Now, instead of like identity x in this identity of x, now in pivotal category is going to be like this. Or when we have fx to y, we're going to write this. But when we have dual, we reverse instead if we write either we write dual of an object and put a lower usual arrow, or we write instead of dual, we write object and reverse the arrow. That's the point. So let's look at this example. If f is a morphism from x dual tensor y to u tensor v dual tensor w, then we can denote it as either one way to denote as everything going down, x dual y u v dual w. That's the usual way of doing. Or we can get rid of this and do this up, or get rid of this or do this up. Or put dual in here and make this up. So they're all equal. They're all equal representations. So in pivotal categories, we have a notion of arrows on our diagrams, which makes this simpler as we will see now. Because remember, evaluation of x is then from where to where? X star x to 1. Right? Instead of this, instead of putting x star everywhere, we just put an arrow and an x. That's enough. And for all of them, it's going to be the same. It just reduces number of labelings that we do. The arrows are very useful to denote duals. And duality identities in pivotal categories are even simpler. Okay, now before duality identities were like this, right? This is kind of a duality. X and Y are dual. These are the kind of conditions. But now they're even simpler with the fixed duality data, kappa and cap. And again, dual of a morphism is much simpler, using evaluations and co-evaluations instead of all composite. This in general, when we write this as algebraically composition, then we need to use composition of 3 maps. Like identity of y composition co-evaluation, and identity of y composition f composition identity of x, and then evaluation composition identity of x. And similarly, this is equal to co-evaluation tensor product with identity of y, composition identity of X, F, identity of Y, and composition with identity of X, co-evaluation, evaluation, tensor with evaluation. And the lemma is that when we have a pivotal category, and the morphism in C associated with generic C-colored Penrose diagram is invariant under isotopy, and deformation of the vertical segment under these moves, these zigzag moves, and the transformation pushing all the morphisms of boxes or cups and up and down. And the lemma says isotopic C-colored Penrose diagrams represent the same morphism in C. So what we have is a representative in the object in C. It's independent of isotopies of these diagrams in R2. Next, we define trace of endomorphism. If we have a pivotal category, when we fix an endomorphism, that means a morphism from object to itself, that its left trace is this composition. Evaluation composed with identity of X dual with F, and co-evaluation. So we are reading co-evaluation identity of X dual with tensor product with F, and then evaluation. This is the left trace, and the right trace is the dual of it. And they are both elements of endomorphisms of their closed diagrams. Remember, we don't denote one, they go from one to one. Look at it. Yes. What is a colored? Yeah, okay, I did not define this, but what is a colored Penrose diagram? Is Penrose diagram are those whatever I draw at the beginning. They're all called Penrose diagram. Penrose is the one Penrose introduced this diagram calculus. C colored one is the one that we color them by objects of element of like we color strings by objects of objects of the category, and boxes by objects of the morphisms. That's what does it mean to be C-colored. And a Penrose diagram is a diagram. I should have said at the beginning that they're initially the work of Penrose initiated this. So we may have some diagram, some boxes and things, and then we can make it C-colored diagram by assigning some relevant things. And this is duality, there's a co-duality, G, H, and this is kind of a C-colored Penrose diagram. And this, so we have some diagram in R2, and then we associate it to some morphism in C. This morphism is independent by these isotopies. That's what I said. Okay, I was talking about left traces, left and right trace, which are using co-evaluations and evaluations together with, in the middle, identity and F, or F and identity. It's like taking a map and gluing the strings up and down in left or right. Gluing from the left or gluing from the right. And they're endomorphism of one. So in particular dimension of an object, okay, we know dimensions of vector spaces, maybe dimensions of projective finite type modules. But now in a pivotal category, we are defining a dimension of an object. So left dimension is trace of identity. This is left trace of identity of X. So this one is instead of F, we put identity X. And same for dimensional right dimension. Sorry. And right dimension of an object is the right trace of its identity map. Identity X. Okay. And a spherical category is a pivotal category. So we have duals. whose left and right traces coincide. So that means for any endomorphism, we have its left and right duals. Remember, they are elements of I need to write that slow, otherwise they're endomorphisms of the unit object. So they are the same endomorphisms of the unit object in a spherical category. Then we have left and right traces equal, and that's we call the trace of a morphism. When we have a spherical category, then we can define the trace of a morphism. Okay. We don't need to specify left or right. So in particular, we have a dimension of an object, which is the trace of the identity map. Okay. And lastly, before finishing the first part, now before all of the things we had before without traces equal, we had the diagrams are independent. The diagram that we associated, the morphism that we associate to a diagram is independent of isotopies of R2. But now, if C is a spherical category, you may ask, where does the name spherical come from? Why it's called spherical? This is kind of a motivation. Then the morphism in C represented by C-colored Penrose diagram. So we have some diagram colored by morphisms and objects of C without free ends. So what does it mean? This have free ends. The without free end is like having endomorphism of one. They're kind of, okay. They're like diagrams like this. Maybe here we have, okay, F. This is a diagram without free ends. Right? It's an endomorphism of unit object. When we have such a thing, if it is spherical, then this diagram is invariant under whatever we associate in the category as a morphism, as endomorphism of one, is invariant under isotopies in the two-dimensional sphere. We extend isotopies from R2 once we have this left and right trace equality to isomorphism. Why? Because the only thing one needs to check is from R2 to R1. Like we have, let's say, so we have some diagram in here. It has some boxes and things, whatever. We can pull some part of this string on the right, right? Okay, and this is the whole thing. Then we can take it back in here, and then we can form, instead of this, we can form this one. Right? That's the right trace equals left trace. That's precisely this move on R2. We cannot do this on R2. We need this point at infinity to be able to do this. And examples are like, I should say not mod, but maybe proj. We need to have those. And these categories are examples. So this is so far where we are. And maybe after a 10-minute break, second part will be kind of shorter a little bit. Maybe we can take 10-minute break and then continue. Sorry, we have a question. Could you example to better understand the dimension of an object in a spherical category? Yes. If we consider finite dimensional vector spaces, if I pick an element, then its dual is just it's a linear dual. And when we form this object, so we have dimension of an object is this. And left or right doesn't matter. And evaluation is just usual evaluation and co-evaluation. The inverse of an evaluation is kind of a, where we choose a basis. Um, omega is 1. Sorry. We start is like it's going EI, sir EI. And this is maybe, but this is going to be co-if. Co-if B. It's just a co-if composed if. And that's going to be it's precisely dimension of an vector space. Or let's consider this category G, whose objects G is a group. Objects are elements of G, and morphisms are like G. Let's say G prime. So under tensor product, what is a dual of an object? If you pick an object, its dual is going to be G inverse, right? Because it's their tensor product. It's just because G tensor G minus 1 is just E. And evaluation and co-evaluation is, remember, they're going from co-evaluation goes like this, goes from here to here. This is the identity element is E, and evaluation goes like this. And they're inverses. So, and then, sorry, this is inverse, but this is E. So they are precisely identity. And their composition is just identity. So every object has one dimension 1. So this is an example. So it is this formula, co-evaluation of, let's say, object X and evaluation. This diagram. Oops. This lower part is co-if if it is labeled by X, co-if X. Sorry, my iPad is behaving. X, and this one is if X. This goes from 1. This is the last time. That's great, and I continue. V answer V or X. And goes from X to 1. When we compose them, it's a 1-to-1, and that's in these categories are 1-to-1 is just K, and it's okay. But it doesn't have to be a number until now. We will introduce them, but it doesn't have to be a number, right? In this case, why it's a number? Because home, this is identity G, but they're times K. This free module of rank 1 generated by this. This is still linear. That's K. Otherwise, it doesn't have to be a number because we haven't introduced linear categories. Okay. What is a braiding? Is that another question for continue? No. A braiding in a monoidal category is a commutativity constraint. Remember, associativity constraint is like it's kind of replacing associativity with some coherent isomorphism. Now we have a braiding which replaces commutativity relation of taking tensor product or tensor product operation, and like is like asking is commutes or not, and if it commutes up to this braiding. And a braiding in C is a natural family of isomorphisms from X for any pair of objects is a natural isomorphism. X tensor Y to Y tensor X, and it satisfies a condition. And these conditions are given by these three equations, these two equations. And the first one, instead of looking at it, it's like, let's say this is x, y, z, and y, z, x, y, z, y, z, x. Okay. Now, if we look at this one, no, sorry, this left-hand side of the equation, swapping x and object y tensor z. Okay, this is one object. So it is precisely this one. Left-hand side of the equation is this one. Just braiding x with this object y by z. We consider this as a single object. But this is equal to, we don't have to consider a single object. First braiding with identity on z, and first braiding with x and y, with identity on z, and braiding x and y first, and then going identity on y and braiding z and x. Okay, identity on y and braiding z and x. And the other one is similar, what, the other direction. So geometrically, this braiding makes sense. That's very common. It's like braiding data. A braided category is a monoid category is endowed with a braiding. So it's like, again, it's kind of a structure. Monoid category is braided if there is a braid on it. There is this specified natural isomorphism going from identity, so going from swapping to morphism to objects, going from identity to swapping to objects. So, and a braided functor between braided categories is a monoidal functor that compares this braiding data. Remember, we have braiding on the target. We can apply first braiding, and part of the data of the functor. Remember, monoidal functor is triple, f0, f2. F is this functor first, and f0 is a morphism. F0 is a morphism from identity of C to identity of, sorry, F of identity of C to identity of C prime. And F2 is a morphism from F tensor fx tensor f of x to f x tensor y. So first we can apply this f2 and then apply image of a braiding, or we apply the braiding in the image and then apply f2. Otherwise, and they must be equal. A braiding is called symmetric if we have this commutativity relations. If we apply 2 times the braiding, then it becomes identity. So geometrically, if you like, it says if we have a symmetric braiding, then there's nothing commute. It doesn't measure anything about braiding. A symmetric monoidal category. A symmetric category is a monoidal category endowed with a symmetry. Okay, being asymmetric is a property. Okay. And an example. Now we can give a full definition. A three-dimensional topological quantum field theory is a symmetric monoidal functor. This is due to Atiyah. This is Atiyah and maybe Siegel. Siegel formulated axioms for conformal field theory. Inspired from Siegel's work, Atiyah defined axioms for a topological quantum field theory. There are 5, 6 axioms. When you put them all together in the current language in quantum algebra, it's precisely equal to these 3 words. a symmetric monoidal functor from cobordism category to the category of vector spaces. Okay, here, like this is a three-dimensional surfaces and cobordisms. And vector spaces and linear maps. Just to remind you again. So what is a here? What is a monoidal structure? Is taking disjoint union of manifolds. What is unit? Is empty surface. Empty manifold is a manifold of all dimensions. Here is taking tensor product of vector spaces over, let's say K field K, and unit object is just the. So what it does vector space. It sends surfaces, oriented surface to a vector space, and then linear maps to cobordisms in a way that coherent to the source and target relationship. And it respects the gluing, because gluing in this category is composition. So whenever we cut, like we have maybe, let's consider 3D. Again, I have sigma prime. There's a little bit digression, but I will not go further. And then let's say we have a functor z. Then z gives some vector space here, and z gives some vector space here to these objects, right? And this is a w. W is a three-dimensional cobordism, so it's a morphism in this category. So its image is going to be some linear map. But let's say, I don't know how complicated it is. Maybe very complicated three-manifold. There's some main thing goes on, but I can cut maybe some codimension one submanifold, which is called sigma double prime. But now I get one, right? I write this W is now W prime glued W double prime along the double prime, right? But now this says this diagram factors through this one. That's what I mean by these morphisms behave well under gluing. When we cut, that means cutting in cobordism category means you write your initial morphism as a composition of two. Okay, W is composition of two. That means in this composition, Z assigns. Okay, Z is in the Z assigns Z W prime, and Z assigns here Z prime. And this diagram colors. That's what I mean by quantum. That's what is called quantum. Why is quantum numerals behave well under cutting and paste operation? Well, let's move on in the algebra part today. It's algebra. Well, next we have seen before the Penrose calculus, usual calculus in R2. Now our diagrams, when we introduce braiding, we are not in R2 anymore. Our diagrams are in thickened R2. Our diagrams are in R2 because we need to encode the braiding data, right? And then this three-dimensional thing, the slice R2 cross I, brings out more relations and more forms. So in this case, this notation, the braiding, remember we are reading from top to bottom. This is a morphism from X tensor Y to Y tensor X. And again, let's consider our category C pivotal. We have arrows. So remember, maybe I write again. No. X right answer X. And yes, and then that's how we denote. This is the notation for the braiding, and its inverse is inverse braiding. Okay, remember this is a natural isomorphism. All of them are, all components are isomorphisms. And we have now 5 moves in relating these diagrams. Like one is going from 1 and then reversing. The other one is McMaster 2, and they have all inverses. 1 or 2, and then 1 is slice. No, this is kept. We move this and slide this back. And our 4 is sliding this front of homomorphism, our naturality, and our 5 is sliding behind over a morphism. This box is some morphism in this category. And one can put arrows. And if C is a braided pivotal category and 2 C-colored McMaster diagrams, so what do I mean C-colored? The strings are labeled by objects of C, boxes are labeled by morphisms of C in coherent way that we have seen above. And plus, when we have braiding, braiding is encoded as shown above as like this. That's a C-colored McMaster diagram when we have 2 of them. And if 2 of them are related by these moves, except the first one, okay, then they denote the same morphism. Okay? In this curly bracket, they denote the same morphism. So you have some diagram, so you put labels on them, C-colored labels. If they are related, the diagrams are related by this one, the corresponding morphism in the category are the same. That's independent. But we don't say the first one, okay? Because the first one has framing information. It's not independent of framing. And moreover, if C is spherical, not only pivotal, but spherical, we have this moving back, then we can add any diagram without free ends, then we can do the same statement for 1. And how do we do this? Remember, we have this diagram on a sphere. Okay? How do we make this part, like what is this? How can I bring this part to this position? Okay, that's remember the first part. Bringing this to a straight line. That's precisely making this into this one. And that's precisely doing this, taking this thing and pulling it cover back and then bring it back. That's precisely that's movement. So that's why we need free ends to do this. Otherwise, it doesn't help. This can happen, but if there's no free ends, we can just pulling operation, the trace operation, the left-right trace operation. Now this brings us to the twists and ribbon categories. Yes, these are the moves that they generate. These moves and their inverses generate the moves. That's how we define isotopies of diagrams in, where did I write? R2 cross I. Okay, what is a twist? A left twist of a category is a family indexed by objects of the form. It's written like this. So I didn't write it what it is. It is a map from, you can see it goes from here x to x, right? And the diagram comes like this. So this goes really from x to x. And how do we write? We write it, if we try to write, we can slice it in this middle. So it is, here we have co-evaluation, if you pay attention. Here we have co-evaluation. Co-ev x, maybe tilde, maybe don't tilde, I forget, and identity of x. Right? I'm writing this morphism, what it is. It is composition. Now I wrote this part. Okay. Now I have what here? I have this x, right? The arrow going up. But that means identity of x star. Oops, this is tensor, not composition. Tensor product with tau x and x, right? And composition. Now I wrote this part. And composition, I wrote this part. Evaluation of x, maybe evaluation tilde, I don't remember. Tensor product with now this is coming like this, identity of x. Okay. This is definition of left trace. So this is reading a morphism from a diagram. You can see it's super easy to draw in here, but when you write it down, it's composition of 3 morphisms, and it's well, not extremely trivial, but that's the really importance of diagrams. It's very simple to see. That's whenever you say twist to a random person in quantum topology, quantum algebra, they draw this diagram. Nobody memorized this. From the diagram, it's writing this down is a minute. So graphical calculus, that's what I want to say is graphical calculus is very, very important and useful and important in this field. And similarly, right twist is defined like this. And you can see the orientation here +1, or this one is -1. Let's see. This says yes. This intersection of, if you not theory, like this is +1, and this is going to be -1. So they're different framing. Well, and they are natural transformations, natural isomorphisms, and their inverses are given by this. Okay. It's not that hard because it's again it's just adding a frame or removing a frame. Okay, a ribbon category is a braided pivotal category whose left twist and right twist equal. And this is called the D twist of C, and the fact is that dual, it's self-dual. Dual of a twist is the twist of the dual. That's slogan. So in short, ribbon category is a category where left twist and right twist are equal. Now we can extend our previous theorem, which I didn't prove, but the proof is one can find it's kind of lengthy, a little bit argument. But proof can be extended to ribbon categories. Before we had braided pivotal, and we had invariants of our diagrams, the morphisms that our diagrams gives in our category. Under 2, 3, 4, 5, they're invariant, they moves. But now, when we fix the ribbon category, when we upgrade from pivotal, braided pivotal to ribbon, then we can add one as well. Okay. Now, how does the proof go? When we have this diagram, this is precisely, when we add it, it's just identity, and then again, they're inverses of their duals or themselves. It's just twist. Twist is the kind of frame measuring. And next one is all ribbon categories are spherical. That's corollary of this theorem. Let's see how this is. This is one of the things, maybe one flavors of graphical calculus. I did it before for dualities and non-degenerate pairings and their inverses, uniqueness of them. This is another proof, quick proof how to do it. Like here, we start with a trace of a right trace of a morphism F. F is an endomorphism of an X. Okay, it's coming here. It's really, it goes from F, really goes from X to X. Let's name this color, this string colored by X. And then we can pull this back here to this. And then we can do R2, right? Right MS to R2. And then next, we can use naturality of this. We can use naturality of the braiding. Right? That's, we can slide this here. That's precise. I didn't go into that detail, but naturality of braiding. You can apply braiding first and then morphism. And then you can apply braiding, you can apply the morphism and then braiding. It's naturality of the braiding. We can move it in here. And now we can pull this diagram to the left. Like we can do plane isotopy in this case, and then move F one more time to here using braiding, naturality of the braiding. In this case, we obtain this diagram, but then this is precisely by R2, I guess, R3. This again is naturality with respect to braiding. We can move this over this braiding, and then we get this one, which is the left trace. So using this Ri moves and R1 moves, here we use the fact that is R1. Ribbon, the fact that we use this assumption. We have ribbon category, that means this is identity, and then we have this. So it's a really nice, cool tool. On the other hand, writing this as an equation is way more messy. Okay, one of the main main object in quantum algebra is what is called fusion categories. But fusion categories again involve it is bunch of categorical definitions. We need to introduce. Let's start. A category C is k-linear if for every object the home set is left k module. These home sets are not sets, but now they are like linear objects. They are left k modules, and such that the compositions are k bilinear. And a functor is between k-linear categories is k-linear if its action on home sets is k-linear. Remember when we have that's what it means. F of x and f of y. This is this is a left k module. This is a left k module, and then f being a k-linear functor means this is between two left k modules is a k-linear one. Now we need to make sense of a direct sum in a category. How do we do that? We have tensor product of maybe vector spaces and things we already introduced by monoid product, but direct sum is like we build it in the category. And how do we do this? Given a finite family of objects in the K category, and then we call an object is called the direct sum of this family. If there exists a family of isomorphisms, this is, remember, oops, this is not the alpha. These are projections you should have in mind. We are writing direct sum in linear algebra or in algebra in terms of projections and inclusions. So remember, inclusions followed by projection is chronicle delta of identity. But taking sum over all projections followed by inclusions, it gives the main object identity. Okay? This equality is characterization of direct sum. Okay? When we have a direct sum of an object in an algebraic category or in an algebra, when we take direct sum of vector spaces, we have projections to each component, and we have inclusions. And these two equations are precise characterizing way of projection. That's the way that we define direct sum of objects. And the category is called additive if it is closed under direct sum operation. So every finite every finite object, every finite family of objects has a direct sum. So an object in this category is called simple if its endomorphisms is K. Okay, remember this means now if it's pivotal, dimensions or traces belong to K. Because remember, dimensional trace of homomorphism is always an element of endomorphism of one, which is when when the unit object is simple, then it's just a number. A monoidal K-linear category means K-linear category and the monoidal product of morphism is K-linear. Expected. And prefusion K category is a monoidal K category such that there exists a set of simple objects. Okay? Remember, a set of simple objects means everything in here, its endomorphism is just isomorphic to K, free module of rank 1. Okay? I is a set of simple objects satisfying the following conditions. The unit object belongs to I. The unit object, that means unit object is simple. Then we pick two different elements on I. There's no morphism between them. There's only zero morphism. This is not empty, but zero. Okay? Because remember, we are in a K-linear category. They must be K modules. They cannot be. They're not empty, but just a zero module. Okay? Whenever we pick two elements, there's no non-trivial morphism between them. So this is like minimality of I. We cannot consider all simple objects. Okay? If they're isomorphic simple objects, we need to get rid of them when we are constructing the I. And next, every object of C is a direct sum of finite family of elements of I. This is really kind of we are finding the core of a category. Okay? Prefusion categories, like we have a kind of collection of objects. This is kind of, it puts maximality on I. So we have enough simple objects such that every object in the category has a direct sum in the elements of I. But we cannot put all simple objects because we have this condition. This is a constraint that we cannot put isomorphic simple objects because it fails in this condition. Otherwise, it fails in this condition. And plus, the unit object must be simple. This I is called a representative set of simple objects. So this implies for every isomorphism class of simple objects, I must have one. Because otherwise, we cannot get direct sum out of everything. So these simple objects are kind of building blocks of the category under direct sum. And I has this kind of smallest representative of it. A fusion category is a rigid prefusion K category, which is only finite number of isomorphism class of objects. So prefusion category is a rigid, fusion category is a rigid where I is finite. That's what it says. But in general, we consider pivotal. We consider fusion categories and pivotal. Okay. And now, before we defined dimension of an object using traces, evolutions, and co-evolutions, if it is, in fact, we define left and right dimensions of an object, and if the category is spherical, then we define the dimension of an object. But now we are defining a dimension of a category. Dimension of a pivotal fusion category, it needs to be fusion, okay? It's dimension of products of, like, we take the sum over all simple objects, representatives of simple objects, and we take product of, these are simple objects, remember, simple. We fix a simple object in the representative set. We consider its left dimension and the right dimension, and we take their product. And then we take their sum, since I is finite in a fusion category. Okay. Fusion means this is finite. So this dimension is finite. So it makes sense. And one can show this is independent of choice of Y. We can choose different representatives of simple objects, but this dimension is independent. It's really inherent to the category itself. Moreover, if C is spherical, then we have this nice formula, right? Because they're equal. if C is spherical, that we have seen left dimension and right dimensions are equal, then we have a better formula. And the fusion category, definition of fusion is one milestone. The next one is modular tensor categories, modular monoidal categories, and let's see what they are. Let C be a ribbon fusion K category, and theta be a twist of C. Remember, ribbon means left twist equals the right twist. For any simple object I of C, there is a unique invertible element Vi called the twist scalar of I. Why? Because remember, twist like this. For a simple object I, twist is like this, but twist is a morphism from I to I. So twist, like left or right, in this case we don't, because it's a ribbon, it's an element of endomorphism of I. But we know I is now simple, right? So this is K. So this whole twist thing, when we consider simple objects, it's just a number, right? This is going to be, this element here is going to be some Vi times identity. Where identity I, we identify under this isomorphism with 1 in K. These are called twist scalars. They are the ones on simple objects. When we pick a representative set of simple objects, then we define delta plus or minuses as like dimension of traces of this of traces or their inverses, and they can be equivalently for the simple objects, right? We can replace this with Vi plus minus, and then their dimension squares. And this delta plus or minuses does not depend on the choice of I. And the category is called anomaly free if delta plus equals to delta minus, like twisting factors category. And for any two simple objects, I and J, they are different, they're not isomorphic. We associate them a number. This is an endomorphism of 1. This is simple again. This is simple, so its endomorphism is K. We take this, what we do, we take these two objects, we braid them and take their kind of closures. Okay, like we apply braiding and then the other braiding and then take their traces. Equivalently, the diagram looks like this. Or like this is right trace of this morphism, left and right doesn't matter because ribbon categories are spherical. This is equal to this, but these are numbers. So for Sij is just a number. So these numbers, depending on the number of simple objects in here, depending on the order of I, that it's going to give, let's say I consists of n simple objects. Then we get from these numbers an n by n matrix. And this matrix is the S matrix of a category. And the category is called modular if this matrix is invertible. And this is very important in the study of surgery TQFT or within Reşat'ın trial. These categories, modular tensor categories, the theorem is that modular tensor categories give rise to surgery TQFTs. Okay. And examples are like simple examples category of finite dimensional vector spaces, and maybe I should here. Or twisted category, this is finite dimensional simple objects, or representations of quantum groups at roots of unity. So not representation of any group, okay. Let's say, let alone being modular, let's consider fusion category. If it is a finite, it's fine because we need to have, remember, to be a fusion, I must be finite. There must be finite many simple objects, right? That is the condition. That is one of the most important conditions on being fusion. So what in the category of representations, what are simple objects? What are those representations whose endomorphism is just K? It's precisely irreducible representations. And if we consider Lie groups, for example, their representations are mostly characterized by weights. So weights are infinite, so they're not quite. So if it is finite, yes, its character table of a finite group is just there are finitely many representations. So it is in fact when G is finite, this is going to be fusion representation category. But when we have continuous groups, one needs to do a lot more work. Like one needs to deform it, form a quantum group, and one needs to take appropriate roots of unity to get rid of, like there's a trash off and then get rid of most of the representations and left with just finitely many of them in a nice way. And that is what is representation of quantum groups, which is quite involved theory that I'm not explaining. So we are here almost except a single topic, which is the center of a monoidal category, which is very crucial relating to constructions of TQFTs. Let's go over that quickly and then end the lecture. A half braiding of a monoidal category is a pair where the first of the element of the pair is an object of the category, and the second one, what is called a half is half braiding, is indexed by objects of the category, and it's given by like braiding, but that's not quite. We are only considering braiding with A. Like we take an object and we're considering its braiding with everything else in the category. And it's a natural isomorphism is delta multiplicative, which is a tensor multiplicative. And the center of a monoidal category is a braided category whose objects are half braidings. Okay, it's a little bit complicated in the first sight. A morphism between two half braiding is a morphism in the category with the appropriate conditions on braidings, as expected conditions on braidings. It commutes with everything commuted in the condition. The unit object is the unit object of the category with identity braiding, half braiding, and the tensor product is given as expected with an appropriate half braiding. And the braiding is defined by the braiding of the second one. So we take a category, we kind of enlarge by considering all half braidings in it. And in fact, the center of a rigid, pivotal, or spherical category is again rigid, pivotal, or spherical. So not very easy. One is to work this out. And the book, they show me very carefully. Let's see how does it work. Maybe as an X in pivotal category. Let C be a pivotal category. Then what is the duality data? Remember, pivotal category means every object is dualizable, plus we choose left and right. We choose every object admits a dual. Now we need to say CC is also pivotal, we need to put duality data. So what is the dual of this half braiding? As again, we use the underlying duality on the object, and the half braiding, it's given in this form, using evolutions and co-evolution, and its inverse is given by this. Okay, so when we take them, and the claim is this whole data is duality data on the center. And whenever we take a center, we have a forgettable functor, which forgets the half braiding. And when we have a monoidal K-linear category, there's a unique K-linear structure on this center, making this forgettable functor K-linear, and that's the one we consider when we consider it. And there are some results, which the first one says the center of a spherical prefusion K category is ribbon. When we take a center of a spherical prefusion category, we get a ribbon category. But moreover, Mügger's theorem says when K is algebraic closed field, and C be an additive pivotal fusion K category with non-zero dimension. This is like when this is car of K is 0 by theorem of Ettinghoff, Nikschik, and Ostrich. If this is 0, then such categories are always dimension is 0. So we don't need this condition when the characteristic of K is 0, is 0. Okay, but otherwise this condition is needed, it's essential. Then the center is additive pivotal braided fusion K category, and its dimension is the square of the dimension of the original category. So when we start with an additive pivotal fusion category, its center is additive pivotal braided fusion. And under the same assumption, if C is spherical, then its center is modular K category. So the point is, when we have spherical, oh, I'm sorry, I cannot write. My iPad is there's a problem. But the slogan is, when we have spherical fusion category, its center is modular tensor category. And what's going to happen in this big picture in the series, or in the notes that Daniel put into the messages, that the notes that I wrote with Alexei visit, the point that we want to make is the work of Alexei and Vladimir is spherical fusion categories gives one TQFT, and modular tensor categories give another TQFT. And in the algebraic side, there's a center construction, and there's a certain construction in the topological side that shows that the corresponding TQFT is kind of equivalent with this operation. Like there's a relationship in the algebraic side and also topological side, and that's given by the kind of center construction. And that's all I want to say, and thank you for your attention.